Hello, everybody. Welcome to the Logic practice page. So as we start into phase two, we're going to be doing a lot of work with logic this unit. So I thought it'd be good to start out with a definition of what a logical argument actually is. It's the process of explaining how a conclusion was reached with certainty. So that's different than just a normal argument, which would take off the last two words, where an argument is just the process of explaining how a conclusion was reached. So not necessarily with certainty in an argument. This chapter, obviously, we're going to be building the idea of logic and how it works. So just for now, I want to start out with you practicing making an argument. So just any argument explaining how your conclusion is reached. And the argument I want us to try practicing with is thinking about how the United States should generate the electricity that our modern society requires. So take a few minutes and first just write down some ideas about that, and then try to construct an argument. So explain how you reach your conclusion of how we should generate the electricity that we need. So go ahead and pause and take a couple minutes and try to do that. Maybe do a little bit of research if you need to about different options, or if you already have done research on this topic, then just write down a sentence or two that explains why or how you reached the conclusion that you did. All right, so here was just kind of my thoughts on it. I listed out some of the different options we currently have: coal, oil, hydroelectric, natural gas, solar, wind, geothermal, and there's certainly many more than just what I've listed here, but these are the ones that came to mind. And so as I kind of thought about that for a minute, my thoughts started drifting towards reducing the impact on the planet. And my argument that I constructed said, as technology continues to develop and become more affordable, we should try to utilize that tech to reduce our impact on the planet. So that being an argument is telling you not just that, hey, we should try to stop hurting the earth, but it tells you why and how I arrived at that conclusion. Now, your conclusion or your argument might be completely different than mine, and that's perfectly fine, right? I'm not here to teach you that we need to stop hurting the earth, right? Like, I'm trying to help you build arguments and understand how a good argument is formed. So whether or not you agree with this statement is irrelevant, and whether or not I agree with yours would be irrelevant. It's all about crafting a statement that explains your reasoning well. And as we build throughout this chapter, we're going to do that with more and more rigor so that our arguments aren't just consistent and clear, but hopefully we can reach our conclusions with certainty is what we're going to start trying to build towards. So as we do that, there are things called logical fallacies. Fallacies are common errors in judgment that undermine the logic of your argument. So you want to try to avoid these things, right? So what I've done here is provided 7 examples of logical fallacies. And over here are 7 logical fallacies. So spend a couple minutes looking these things up and trying to figure out which logical fallacy goes with each example or with each bad argument. So go ahead and pause and try to do that right meow. All right. So, looking at the very first one, solar power is good because it's better for the environment. So the bad part about this argument is that it uses kind of a synonym there. Solar power is good because it's better. This is what's called a circular argument. And it's circular because it restates the argument rather than proving that the claim is true. Simply saying that it is better is just restating that it's good. You didn't really get anywhere in this argument. You just kind of circle back to your original premise or your original statement. So that's the idea of a circular argument, and you definitely want to try to avoid that as you're making arguments. Next one hopefully wasn't too bad because the words are in it. Either we stop using coal or we destroy the earth. Yeah, that's an either or fallacy. So the idea behind either or is that it oversimplifies the argument to only 2 apparent choices, so that you only have 2 apparent choices in it. It ignores the range of possible options in between. So like, stop using coal or destroy the earth. Well, yeah, those are 2 extremes. But what about everything in between? Maybe we find a way to purify coal so that it doesn't produce CO2, right? There are many other options in between those 2 extremities. The next one is an example of a slippery slope. First, they'll ban coal, then oil, then gas, then cars. What's next? Oh no. So, this is the idea of a slippery slope. And in a slippery slope argument, what it tries to do is draw a connection from one point to the other. It doesn't necessarily have to happen. It's saying that if one of these things happens, all of them will happen. And that's just not necessarily true. We could ban coal and then just find a way to replace generating energy without it and not need to ban these other things. Also, watch out for things like this where they just use ominous words like they, like who? The government? Okay, also, who is the government? Are we talking about individuals, a corporation? What do you mean by they? Watch out for ominous terms like that are meant to try to scare you, spook you in their arguments. People who don't support solar power don't care about the earth. This one is actually one of the ones that is used well. It's still bad, right? But it's often camouflaged in an argument. You won't notice that they're using this against you. It's called the straw man fallacy. And it comes from the idea of like reducing a person down to a scarecrow, or like when they were in the medieval times using like practice dummies to shoot arrows at and stuff. It's the general shape of a person, but it's hollow inside. It's not, there's nothing there. So what it does is it oversimplifies an opponent's argument and then attempts to attack that hollow example. So here what they're doing is saying that if you don't support solar, the only reason you wouldn't support solar is that you don't care about the earth. Like, that's not necessarily true. There are actually reasons not to support solar. Like, for one, it's kind of expensive. There are other options, right? There's a discussion to be had there about whether or not we should use solar power, and just reducing the person down to saying, well, you don't care about the earth. You've hollowed out their argument and made them back themselves into a corner where now they have to fight back about why they care about the earth and don't like solar power. So that's why that is considered a fallacy. My next one is definitely my favorite. It's only lazy hippies that don't care about renewable energy. This is an example of what's called ad hominem. And I don't know if this is what it means or not, but what it makes me think of when I hear the words are at a person. And because that's kind of what it is. Ad hominem is where you attack the character of the person rather than the argument itself. And it is used constantly on this little thing called the internet. If you've ever seen it, if you've ever been online, you know what I'm talking about, where somebody just like, well, you failed geometry class, so your opinion doesn't matter. Something like that. Like, it reduces the argument down to the person rather than what they're actually talking about. It is probably the worst fallacy that you can commit, because it just completely derails the conversation and makes it personal rather than logical. All right, so if we ban coal, what are coal miners going to do? Now, this one's actually really interesting. So this is called the red herring fallacy. And it comes from literature. So a red herring in a novel or in any kind of story is where they put forth a character or an event or something that is meant to purposefully distract you. So like, this guy clearly is the murderer, but it's not really him. It's just there to make you think that is, and then give you a twist, right? So the way it's being used here, the way the fallacy is used, is that it brings up this idea of coal miners who are a part of banning coal, right? They will be, anybody who is currently a coal miner will be affected by the banning of coal. So it isn't irrelevant, but it's definitely not the critical point when we're talking about how to generate electricity. This is a much bigger topic than just these people and their jobs, right? You can't base this large of a decision off of this one attribute of the conversation. So when you turn the conversation or the argument towards a specific piece of it and really try to focus on that, that's an example of a red herring fallacy. And then the last one, dirty, filthy coal should be outlawed. So this one is called begging the claim. And it's kind of like the first example, circular. Does is it shows where the conclusion that should have been proven using the claim. So you're taking the claim and trying to prove your conclusion. It uses the conclusion to try to prove that, like, it's going to be outlawed because of this stuff. If you started by explaining how coal is dirty and filthy, then you could logically argue that it should be banned, like saying that coal produces this much CO2, this much CO2 in the atmosphere causes this effect. This effect is bad, therefore it should be outlawed, right? You can that's a solid logical argument right there, where you start with a premise and you end at a conclusion. This, however, is simply relying on the emotional tug of saying that it's dirty and filthy, and you know what I mean by that, right? And then let's just outlaw it. Like, you're begging the claim, you're making a final statement without actually going through the rigor of proving whether or not that thing should be true. Okay, so this is some of the idea behind arguments and logic that we're going to be building off of this entire chapter. So a couple more vocabulary words that I want to make sure you know is, first off, you'll hear this used all the time if you haven't already. A conjecture. It's just a statement that has not been rigorously proven yet. Another way of talking about it is just an educated guess, right? Where you aren't just randomly shouting out an answer. You have some reasoning behind it, but you're not sure if it's true yet. You're not sure if it is 100%. So you're kind of putting it out there, not positive yet. It's something to work off of. And induction is kind of similar. So induction uses reasoning to find apparent patterns and predict what comes next. Now, the problem with induction is that it's never 100% certain in the real world, that you never have all the data that's available in the entire universe. So you can't be certain that you know the whole pattern yet. Maybe some new information emerges that changes that pattern and makes you reevaluate what you think will be coming next. So it's useful, but it's definitely not the end all be all. We'll get to deduction, which is much more ironclad in our next lesson. So for right now, I want you to try to use induction to decide what comes next in each of these patterns. So go ahead and pause the video and try that now. All right, so as you start looking at the first one with the triangle, so we start with one big black triangle, then we put a white triangle in the middle that splits it into three smaller black triangles, then we put a white triangle in the middle of each of those that splits those into three triangles. So if you're counting the black triangles, how many black triangles there are, you go from 1 to 3 to 9. That looks like it's multiplying by 3 each time, and it makes sense because each triangle is getting split into 3 parts. So if I take 9 and get 3 triangles out of each of those 9 black triangles, I'd end up with 27 itsy bitsy little black triangles. What number is next in the sequence? So negative 40, 20, that's being divided by negative 2, divided by negative 2, divided by negative 2. So if I keep that going and divide by negative 2 again, it's going to give me negative 2.5, half of 5. And also the sign is switching back and forth from positive to negative, positive to negative. And finally, flipping a coin 10 times, and every single time it comes up head, what's going to happen next? It's still a 50-50 flip, people. All right, so this is one I guarantee there's people out there that both said, or some people said it's definitely going to be heads. Some people said it's definitely going to be tails. Neither are true. It's still, the previous flips don't affect what happens next. People who are saying that it's definitely tails, like we're overdue for a tails, what you're thinking there is that what are the odds of sitting down and flipping a coin 11 times in a row and getting heads every time? You're right. That is very unlikely. It's very, very unlikely to happen. But once it's happened 10 times, you still have a 50-50 chance of it being heads or tails on the next flip. It's not talking about the total number. What's the odds of getting 11 in a row? It's just saying what's the odds of the next one. Every flip of that coin is 50-50. We'll spend a lot of time at the end of the year looking at probability and addressing misconceptions just like this. But you can hopefully see where induction can fall short, right? Like, let's say the next triangle only had, 3 triangles again, or the next number only was negative 10. So in that case, I'd have to reevaluate the pattern and say, well, does it only go to a certain point and then turn around? Like, what's the pattern here? What is actually happening? So that's the idea, that you're never 100% certain because you never have all the data. You have to make an educated guess off of the information that you have available. All right, so induction's a good place to start, and we're going to work with that today. And the next lesson, we'll start working on deduction that's a little bit more ironclad. So a few more vocab words. True and false. Whenever you hear the words true and false, it's referring to a singular statement. It is true if it reflects reality. It's false if it doesn't reflect reality. Like if I flip a coin and it's heads and I say it's tails, that would be false because it doesn't reflect what actually happened. Now, when we use the words valid and invalid, that's talking about an argument. It's only valid if the argument follows the rules of logic or if it's logically consistent. So that's what we're really going to be diving into next on the next lesson is what does it mean to be logically consistent? What is logical and what is illogical. What statements can I take information from and draw new information, and what wouldn't work? And one way of finding if something is true or not is by looking at for counterexamples. So a counterexample is something that opposes a theory, and you only need one to disprove it. So if I think that it's going to be heads and tails every time or something like that, and then it comes up tails once when I thought it'd be heads, that is a counterexample. Or if I say, like on this next example, that it's always going to be true, but I'm able to find a single number it doesn't work for, boom, it's no longer true. It can work a billion times, but if you find one time it doesn't, you've disproven the theory. You only need one counterexample to disprove something. So go ahead and pause now and see if you can determine whether or not this equation, taking a number, squaring it, and square rooting it, will always give you back that same number. Start with a few examples I provided, and then try other numbers to see if it's always true. All right, so you might have been able to tell just by the way the question was phrased that this boy was going to turn out to be false. But let's figure out how, because this is a really good way of approaching validity in general, finding out if things are valid or not, true or not. So when I first start with a couple examples, 1 squared, 1 times 1 is 1, and the square root of 1 is 1. 2 squared is 4, the square root of 4 is 2. 3 squared is 9, the square root of 9 is 3. So it looks like whatever number I'm plugging in, I'm getting back. If I square a 2, I get back a 2. If I square a 3, I get back a 3 at the end. Here's where it breaks down, is if you take a negative number in there, is it true for all numbers? Well, no, not negatives, because when you square a negative, you get a positive. And then if I square root that positive, I get back a positive. So I plugged in a -1 and I got back a 1. That is a counterexample. Therefore, it is false, right? So that's how you can use counterexamples, even though it worked over and over again. I could have had you keep going with 4, 5, 6, 7, 8.9 would have worked, right? Any positive number would be fine, but negatives is where it breaks down and falls apart. So this is the idea of a counterexample and how it can be used to disprove a statement. Now, looking at valid and invalid. So I'm starting to build you up towards the idea of proofs and the way that they're going to look using this givens and conclusions, things we're trying to reach. So what you do here is you read through the first, the givens, the given or givens, and try to decide whether or not you can determine that the conclusion is true or valid in this case, based off of the information that was given. So go through, honestly, just use your common sense on these, right? Just use your judgment, make a conjecture for each. I'm not looking for right and wrong. This is completely zero stakes. It's just, try it. Try thinking through and starting to develop this logical thinking ability. All right, so the first one here hopefully wasn't too much of a brain teaser. It is invalid. Just because something happened for 5 straight years doesn't mean it's always going to continue to happen. In fact, this has a name. It's called the hasty conclusion fallacy. So when this happens, it's that you take a little bit of data and make a giant generalization about it, and that's rarely going to work out well for you. You need a large sample size in order to make large sweeping generalizations like it's always going to be in January. In fact, it's actually not even true that it's happened for 5 straight years. In 2017, the coldest day in Chicago was in December. I looked it up. So this is definitely not only invalid, it is not true as well. The next one also is invalid because this is what's called the converse error. And we'll learn about converse in the next section. But what they do here is they say, all right, if a pet's a rabbit, it eats carrots. Jeannie's pet eats carrots and then tries to work backwards. So this is what's called the premise, the first part, and this is the conclusion. It takes the conclusion and tries to reverse it and work backwards to assert that this must be if that happened. Well, that's not how it works. It's saying if this, then that. Not if this, then that. So when it goes to say that it's a rabbit just because it eats carrots, like, no, it's not. Lots of things eat carrots. Could be a horse. It'd be kind of weird, but Jeannie could have a pet person. People eat carrots, right? That's weird. All right. So those first two are both invalid, but the last two are definitely valid. And here's a couple different strategies you can use to determine or convince yourself that something is valid, that you haven't just tried a couple examples that happen to work, but that it will always work. So what I did here is I took numbers that I knew were divisible by 6, multiples of 6, and then I tried dividing them by 3. And every one seemed to work. So I couldn't find a counter example. 6 divided by 3 is 2. 12 divided by 3 is 4, 6, 8, 10. They all seem to divide by 3 if they divided by 6. So what then I tried to do is say, all right, let's think of some unknown number, some random number. If I divide that by 6, how can I figure out that it also divides by 3? And I thought, well, 6 is just the product of 2 and 3. So if I can divide it by 6, or when I divide a number by 6, I'm essentially also dividing it by 2 and 3. It's the same thing. To divide by these two numbers is the same as dividing by 6. So if I'm dividing it by 6, I actually am dividing it by 3, but also a 2. So if I can do this, then I'll also definitely be able to just divide it by the 3. So that convinces me that this is a valid argument, that it will always work. This one is also valid. So one tool you might try to use is drawing a picture to help you convince yourself. It's not ironclad, but it can help you start getting your reasoning rolling. Here, I actually set up what's kind of an informal proof. We're going to work with proofs at the end of this chapter. But what I said is like, all right, so what it means to be supplementary is that R plus S, angle R and S, have to add up to 180. Well, it's also telling me that R and T add up to 180. If two things add to the same number, then that means they equal each other. If my money is $5 and your money is $5, then my money equals your money because they equal the same amount, right? So I can now say that this equals this because they equal the same number. It's called the transitive property. So if they equal the same thing, just like solving an algebraic equation, you can subtract a number from both sides. You can subtract angle measures from both sides. So if I take away angle R, then I'm left with the statement that R is in fact equal to T, which is what was asserted in our conclusion, that angle T and S are congruent. Did I say that right? Angle S is congruent or equal to angle T. So since I have that, I can assert that this is absolutely true. All right, you've got two practice assignments. This chapter is going to be pretty light on con, hooray, because there's just not a lot of proof stuff on con, which is what we're really building up towards. So take some time, work through those two sections, and as always, email your teacher when you have any questions.